Today we start the dreaded Taylor polynomial. Now, I don't want you to panic. Basically what a Taylor polynomial does is it allows us to approximate a function around a known center. You can kind of think of this as tangent line approximation on steroids. And here's what here is a Taylor polynomial. How we generate it. A Taylor polynomial of n degree, where n is going to be a number of derivatives that we're going to be taking. We'll talk about that in just a few moments. Okay, where n is what's called the number of derivatives, is given as such. The value of the function plus the value of the derivative times x minus c. Now this should look familiar to us. This part right here is a linear function right here. This is what we call our tangent line approximation. So basically what a Taylor polynomial does is it allows us to approximate. But the problem with tangent line approximations, like if I have a curve right here and I want to estimate this point right here, if I draw my tangent line, I have a big error. Well, what if I can make a quadratic approximation? More follow closely the curve itself, I can limit that error more. So that's what Taylor says we can do. And that's what goes on here. We go past a linear approximation to a quadratic approximation, cubic approximation, all the way to an nth degree approximation right here. Now, how we generate a Taylor polynomial is very simple. This is our rule right here. We're going to talk about that today. Okay? That's our rule. Now, this polynomial will closely approximate the values of any function. And I'll give you guys an example. Let the function f of x equals sine of x right here. I want to write a polynomial function that looks very similar to that in close approximation. Now we have to have a center, and that's what this c is for. C is our center. In this case, let's let c equal 0. Now we have a special name for this. It's called a Maclaurin Polynomial, which we'll talk about in just a few moments in the next part. But really what I want to do is I want to generate a polynomial that looks like sine of x. Now how far you want to go is up to you. Let's let n, the number of derivatives we're going to take, equal 6. So what that means is I'm going to take 6 derivatives of sine of x. And I'm going to go and start that. I'm just going to take derivatives. Now, remember, n is the number of derivatives. Now we're starting with the 0th derivative of the function, which is just the sine of x. And I just keep going. The derivative of sine, cosine, negative sine of x, negative cosine of x, sine of x, cosine of x, and negative sine of x. Now, what I'm going to do here is I'm going to use my rule. Now, my rule right here for a Taylor polynomial is going to generate this whole polynomial right here. So the first thing I need to do, I need to find the value of each derivative. In this case, we're going to let c equal 0. So I want to first find f of 0. Well, sine of 0 is easy, 0. The first derivative at 0, cosine of 0 is 1. The second derivative at 0, we get 0. The third derivative at 0, negative 1. And you kind of see a pattern here, I guess you could probably see. The fifth derivative at 0, we get 1. And the sixth derivative at 0, 0. So we see a little pattern right here. Now, after we do this, we're going to use our rule to generate our polynomial. And I'm going to go ahead and write down the rule right down here. So my rule to generate the Taylor polynomial is the following. Pn of x equals the value of the nth derivative at c over n factorial, the number of derivatives factorial, x minus c to the n. Now remember, for us, c is 0. So if I plug this in, I am looking for a 6th degree Taylor polynomial. That's what this says. P sub 6 of x, I'm looking at a 6th degree Taylor polynomial. And what my rule says to do, take the value that we just found, divide it by n factorial. Well, over here, it's just my first term, my first value was 0. Don't need to divide that by anything. but I keep going. My next one now says I'm going to add. It's actually a series. We're going to add. So I go plus, my value is 1 over n. Well, in this case, n is 1, my first derivative. 1 factorial. X minus c, but remember c is 0. So I can just write this as x to the first. Keep going. Plus 0 minus 1 over. This is my third derivative. So 3 factorial x cubed. Again, it's x minus 0 cubed, but you don't have to put down the 0. Plus 0 plus, this becomes 1 now over, now my n is 5. 5 factorial x to the 5th plus 0. And I can simplify that. This just gives me x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th. And I'm going to rewrite that again. That looks nasty. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Now what we're saying is that this polynomial approximates the sign of x. So what we are saying, therefore, is that the sign of x is about the same as x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And we can kind of see that if we were to graph this. Let me go ahead and graph these both right here. If I graph the sine of x, let me just graph the original function, sine of x. Enter. There's my sine function. And let's graph my Taylor polynomial. X minus x cubed, so I can write this as a fraction if I want to, x to the 3rd over 3 factorial, which is just 6, plus, add the fraction again, I can do this as x factorial, x to the 5th, divided by 5 factorial, which is just 120, and I hit enter, and there it is. Now if you notice, now they're not exactly the same, but what's important is near 0, take a look there. They are very accurate. They are very close to each other. And what that means is, let's say I want to evaluate the sine of 0.1. Well, if I don't have a calculator, how can we do this? Well, just like back in the old days, we would use a Taylor polynomial to approximate it. So we can say, therefore, that the sine of 0.1 is about, and I'm going to plug this in, 0.1 plus, minus 0.1 cubed over 6 plus 0.1 to the 5th over 120. And if I type that in my calculator, let's see what that equals. 0.1 minus 0.1 to the 5th divided by 6 plus 0.1 to the 5th divided by 120. I hit enter and I get this long decimal right here. Well, what is the sine of 0.1? Well, if I type it in, the sine of 0.1, take a look at what we get. There's my approximate value. There's my actual value. Wow! Look how close they are. 6, 6, 4, 7. They change, wow, way over here. So this is a great way to approximate values. Now, where do we use this? Well, in calculus, let's say we want to find the antiderivative sine of x squared dx from like 0 to 1. Well, we can't actually solve this one by hand, so what we have to use, we use a polynomial, Taylor polynomial, to do this. And what we would do is, I could rewrite this from 0 to 1. Now take a look here, the only difference here is x is being squared, so I just square all my x's. This becomes x squared. If I square x cubed, we get, what's that, minus x to the 6 over 3 factorial, plus x square x to the 5th, I get x to the 10th over 5 factorial dx. So these can become approximated to each other. Now we're going to talk about this skill later on. Now, so going to part 2, we'll just take a look at a few more examples of polynomials.